Welcome to the last section of Chapter 8, which is 8.5. Today we're going to look at applications of matrices and determinants. And the first thing we're going to start looking at is Cramers Rule. Now, this is a definition from your book. Okay, you can read through that, try to figure it out, that's okay. In our next example, or our first example of this section, I'm going to show you how to actually use this. Okay, so if you want, like I said, you can write this down. You don't have to. I'm just going to show you how to use this and apply it. The only thing that I would like to point out really quick is if you have a coefficient matrix A, coefficient of matrix A, and you have a non-zero determinant, then your solution to that system is given by your x1 term is going to be found by taking the determinant of the A1 matrix, and you're going to divide that by the determinant of your coefficient matrix. Your x2 term, or it could be y or z, is going to be found by taking the determinant of the A2 matrix and dividing it by the determinant of your coefficient matrix, and so on. Again, let's look at our next example. I almost forgot. If the determinant of the coefficient matrix is 0, then the system either has no solution or has infinitely many solutions. So that would be the only kind of thing we have to look out for when we are using Cramers Rule. So we're going to use Cramers Rule to solve this system of linear equations. The first thing I'm going to do is I'm going to write the coefficient matrix as 4, -2, 3, -5, and I need to find the determinant of that matrix. And I'm going to call that determinant capital D. And if you remember, that's found by going 4 times -5, which is -20, minus 3 times a -2, or -6. A -20 minus a -20 minus a -6 is really equal to a -14. So now that's the determinant of my coefficient matrix. I now have to go in, and I'm given that x1, or in this case I'm just going to call it x, is equal to dx divided by d. And these d's are really your determinants. Okay, so I'm going to say the determinant of matrix x divided by the determinant of my coefficient matrix. And this right here is my coefficient matrix. So now what I'm going to do, to find my dx, or the determinant of my x matrix, I'm going to start out and I'm going to rewrite my coefficient matrix, and I'm going to fill in my x terms, because typically my x terms go here, my y terms go here. I'm going to replace all of my x terms with my constants. So I'm going to replace them with a 10 and 11, and I'm going to leave my y terms the same at a -2, -5. And I'm still going to divide that by the determinant of my coefficient matrix, and I already solved that, so I know that was a -14. Now I have to take the determinant of this new matrix right here. So to take the determinant of that, I have 10 times a -5, which is a -50, minus 11 times a -2, which is a -22, and I'm going to divide that answer by a -14. Well, -50 minus a -22 is really a -28, divided by a -14 gives me a +2. So what I just found is that the x solution to this matrix, or this system of linear equations, is really 2. And I'm going to go through and do the whole process again with my y values. So let's go ahead and do that. So now for y, I'm going to take the determinant of my y matrix and divide it by the determinant of the coefficient matrix. And to find that y matrix, I'm going to now leave my x values in there from the original coefficient matrix. So I have 4 and 3, and I'm going to replace the y values this time with my constants of 10 and 11. And I'm still dividing by the determinant of the coefficient matrix, which was a -14. So now when I go and solve the determinant of my y matrix, I have 4 times 11, which is 44, minus 3 times 10, which is 30. I'm going to divide that by -14, and 44 minus 30 is 14, divided by -14 gives me a negative 1. So what that tells me now is that my y solution is really negative 1. And if you go and you double check this point into either one of these equations here, you will see that it will work, or you can graph these equations and it will become the point of intersection. The next thing we're going to look at is how to calculate the area of a triangle. Now the area of a triangle with vertices x1, y1, x2, y2, and x3, y3 is given as plus or minus 1/2 times the determinant of. Now the stuff that we're going to put in the determinant matrix is we're going to place our first coordinate point, x1, y1, in the first row, x2, y2 in the second row, and x3, y3 in the third row. Then our third column will always be 1s. Doesn't matter what your coordinate points are, we're always going to plug in a 1. Now we need this plus or minus here to accommodate the sign of what the actual determinant is, because it doesn't make sense to have a negative area. So if I calculate a determinant and I get a negative number, I'm just going to take the negative of that so that I end up with a positive area. If I end up with a positive determinant, I'm just going to leave it positive. Example 3 says to find the area of a triangle whose vertices are 1, 0, 2, 2, and 4, 3. So I'm going to start out by putting my coordinate points in the determinant matrix. So I have 1, 0, 2, 2, 4, 3, and then I'm going to make this a square matrix by placing my 1s in the third column. And from there, you can do any method that you want to, but I think expanding is probably going to be the easiest way to do this. So when I look at this, or look at my matrix, because I have a 0 in this first row, I'm going to go ahead and just use row 1. And you can use any row or any column that you would like, but this is what I'm going to use just for the sake of this example. Now, what you'll see is up here at the top, I just placed the cofactor matrix for the signs just to kind of help us out. But I'm going to go ahead and expand by cofactors using this row here. So I'm going to have 1, and my sign of my cofactor is going to be positive, or in other words, I'm going to keep the sign of my major, if you recall from the last section. My major, if I cross off the first row and first column, is going to equal 2 times 1, which is 2, minus 3 times 1, which is 3. So this is going to give me a negative 1. Then I'm going to add to that. Actually, let me make this a vertical setup. I'm going to add my coefficient, which is going to be 0 times, and if I cross out the middle row, first row, middle column, I'll see that I'm taking the determinant of 2 times 1, which is 2, minus 4 times 1, which is 4, and 0 times anything is 0. So I'm then going to add that to my coefficient of the first row, which is 1, and I'm going to cross off the first row, third column, and I have the determinant of 2 times 3, which is 6. So, 6 minus 4 times 2, which is 8. So that's going to give me a negative 2. And I know in the third column, or first row, third column, I see that my sign stays the same. So it looks like I have a negative 1 plus 0 plus negative 2 is going to give me a negative 3. Now we hopefully remember from the previous slide that the area was equal to plus or minus 1/2 times the determinant. So in this case, I'm going to have plus or minus 1/2 times my determinant we just found was equal to a negative 3. Since I can't have a negative area, I know that I have to use the negative 1/2. So a negative 1/2 times a negative 3 is going to give me 3/2 square units. and that will be the area of that triangle with those vertices. Another application of determinants has to deal with determining whether or not lines or points lie on a line in the same plane. If you remember, this is called collinear, so we can say that 3 points, x1, y1, x2, y2, and x3, y3 are collinear, or they lie on the same plane, if and only if I take the determinant of their matrix and I get 0. If I get anything other than 0, then they do not lie on the same plane. The next example says to determine whether or not the points -2, -2, 1, 1, and 7, 5 are collinear. So the first thing I'm going to do is I'm going to take and find the determinant matrix, and I'm going to do that by going -2, -2, 1, 1, and 7, 5. I'm going to plug those in for x and y, and just like we did for the area of a triangle, I'm going to make that third column all ones, and then I'm going to expand by cofactors. Now, it does not matter which row or which column you use. I think I'm going to use the second row here just because I have all ones. When I calculate the majors for this row here, I see that when I go to expand it, I'm sorry, I have 1, which is the coefficient, times, now in this spot right here, if I look up here at my sign chart, I see that for cofactors I'm going to have to change the sign. So I'm just going to go in and multiply that by -1 so that I know I have to change the sign, and then I'm going to go ahead and calculate my minor. So if I cross out the middle row, first column, I see that I've got -2 times 1, which is a -2, minus 5 times 1, which is 5. And if I simplify that, -2 minus -5 is a -7. Multiply that by a -1 and I get a +7. For my next cofactor, I have 1 times. Now for this middle term here, I see that my sign is going to stay the same, so I'll just go +1 times, and when I cross out that middle row, middle column, I have -2 times 1, which is a -2, minus 7 times 1, which is 7, and -2 minus 7 is a -9 times +1s is going to give me -9. And if I go and do the third cofactor, I have 1 times, I see I have to change the sign or multiply by a -1, and then I'm going to cross out the third row, second column, and I see that I have a determinant of -2 times 5, which is a -10, minus 7 times a -2, which that becomes +14. So -10 plus 14 is a +4 times a -1 is a -4. So 7 plus a -9 plus a -4 gives me a -6. So I have a determinant of a -6, and since -6 is not equal to 0, I can tell that these points are not collinear. They would only be collinear had I gotten 0 for a solution. Determinants can also be used to find the equation of a line passing through 2 points. Okay, and we do this by taking our 2 points. We're going to call our first spot x, our second spot y. Then we're going to plug in the coefficients or the coordinate points of the 2 points. So I have x1, y1, x2, y2, and again my third column will always equal 1. So if we go ahead at the example 5, it says find an equation of the line passing through the points 2, 4, and -1, 3. I'm going to start out by writing my points in the determinant matrix. We're going to start out with x, y. I know the third row is going to be all ones. And I'm going to plug in my points 2, 4, and -1, 3. And again, I'm going to calculate that determinant. Now, if you expand by cofactors on the first row, you will see that you get x, that first spot for cofactors is going to give me a positive 1. I don't change the sign. And then I'm going to cross out the first row, first column, and I see that I have a determinant of 4 times 1, which is 4, minus 3 times 1, which is 3. So when I simplify this, 4 minus 3 is 1 times a positive, remains 1, and I'm still left with x. When I go and I look at my second spot there, or my second coefficient, I have y. In the middle, I know that I have to change this sign, so I'm going to multiply by a negative 1. And when I do the determinant of the first row middle column, I see that I have 2 times 1, which is 2, minus a negative 1 times a positive 1 will give me a negative 1. 2 minus a negative really becomes 2 plus 1. 2 plus 1 is 3, times my negative 1 gives me minus 3y. And then I'm going to go ahead and do the same thing with my first row, third column spot, where I have a coefficient of 1. I know that spot is going to remain positive. And then I'm going to do the determinant by crossing off first row, third column. 2 times 3 is 6. Minus 4 times a negative 1 really becomes plus 4. 6 plus 4 is 10 times positive 1 gives me a positive 10. So I'm going to take all of the stuff that I just found, or all of the individual pieces, and I get x minus 3y plus 10 is all equal to 0, because I know that the determinant of this equals 0. And that's how I find my equation of the line that passes through those 2 points. The last thing we're going to look at today is a cryptogram, or cryptography. Now, a cryptogram is a message that is written in a secret code. Okay, and we can actually use matrix multiplication to either encode or decode these messages. Now, your book has this chart that I have down below, like all of this stuff here, on page 625 if you want to refer back to it. I will also give this chart to you on a test or quiz. But essentially what's going on is any space in my phrase is going to be represented with a 0. Any letter A is going to be represented with a 1. Any B will be represented with a 2. C will be represented by a 3, and so on. We then have to assign every letter in our message to one of the following numbers. We will then do what we call an uncoded row, and I'll show you how to do all that in our first example that deals with encoding and decoding. So example 6 says to write the encoded matrix of order 1 by 3 for the message, meet me Monday. Because we were told to write these as a 1 by 3 matrix, I'm going to go through and make a matrix as a 1 by 3, and every letter and space is going to be assigned a number from that previous slide that I just showed you. So if you look back, you will see that the letter M corresponds to the number 13. E corresponds to the number 5. Okay, so I just now took into account my first 3 letters. I then have to do my next matrix, which begins with the letter T. T corresponds to 20. I have a space right here, and a space is actually represented by the number 0. And then again, I'm going to go on with the letter M, which we said was 13. I've got my second 3 terms, so then I'm going to go on to my next matrix, where I'm beginning with the letter E, and E corresponds to 5. I have a space, or 0, and another M. And then I'm going to start in with O, which is the number 15. N is 14. D is 4. A is 1. Y is 25. And then I have a space left, so I'm just going to plug in a number 0. Now these right here are what we call our uncoded matrices. Okay, because all I've done is I've given them a number that correlates to a letter of the alphabet. So there really is no nothing tricky behind that. So this would be easy to decipher if I left it as is. Now, I will be given an encoding matrix that will help make it harder to come up with the decoding of this. So the encoding matrix, I'm going to write this down below. So the encoding matrix, and this will all be given to you, is equal to 1, -2, 2, -1, 1, 3, 1, -1, -4. So now if I multiply my encoded matrix, or my uncoded matrix, sorry, by my encoded matrix. So let's write this down. I need to multiply the uncoded by your encoded. Then this will create my coded matrix. And this is something that you can do all in your calculator. So for example, if I look at the first matrix where I had 13, 5, 5, and I multiply that by the encoded matrix of 1, -2, 2, -1, 1, 3, and 1, -1, -4, by multiplying these, I will get a 1 by 3 matrix of 13, -26, and 21. I now have to go ahead and do this for all of my uncoded matrices that I created up above. So if I take the next one, which was 20, 0, 13, and for now I'm just going to call this matrix A, because you should already have that entered into your calculator. When I multiply these together, you get 33, -53, -12. I'll take the next uncoded matrix of 5, 0, 13, and I'm going to multiply that by matrix A, and I'll get my next coded matrix, which should be 18, -23, -42. I'll take the next uncoded matrix of 14, 4, multiply it by matrix A. This will give me 5, -20, and 56. And I'll take the last uncoded matrix, which was 1, 25, and 0, multiply it by A, and get the matrix -24, 23, and 77. So now, what would happen is I want to keep all of these 1 by 3 matrices in order, and if I put them all side by side and I remove their brackets, I end up with 13, -26, 21, 33, -53, -12, 18, -23, -42, 5, -20, 56, -24, 23, and 77. So this list of numbers now essentially doesn't mean anything to anyone unless they have the encoding matrix. Now, if I want to go in and decode a coded matrix or a coded cryptogram, what I have to do is I have to use the inverse. So my last example says to use the inverse of the matrix A, which is the same A that we were given in the previous example, to decode the cryptogram. So now I want to decode the cryptogram. Now, we already know what this is going to say because we've already worked it from the opposite direction. But if I didn't know what this said, what I'm going to do is I'm going to go and I'm going to bracket all of these up into matrices. And they have to be the 1x3 matrices. So I have 13, negative 26, 21. Then I have 33, negative 53, negative 12. 18, negative 23, negative 42. 5, negative 20, 56. And negative 24, 23, 77. Once I have them all grouped together, I then have to take each individual matrix and multiply it by the inverse of A to come up with my decoded matrix. So let's go ahead and keep in mind that matrix A is this right here. Okay, so when I come down here, I'm going to take the first 1 by 3, which is going to be 13, negative 26, 21, and I'm going to multiply it by the inverse of A. And when I do that, you should see that you get 13, 5, 5, and again, please use your calculator with all of this stuff. Then I'm going to take the second matrix, 33, negative 53, and negative 12, multiply it by the inverse of A, and I get 20, 0, 13. I'll take the next 1 by 3, which is 18, negative 23, negative 42. Multiply it by the inverse of A to get 5, 0, and 13. And I'm going to continue on with this. So my next one will be 5, negative 20, 56 times the inverse of A. This is going to produce 15, 14, and 4. And I'm going to take the last matrix at a negative 24, 23, and 77. Multiply it by the inverse, and I'll then get 1, 25, and 0. Now, right here, I have a coded matrix. This is, the inverse is known as the decoding matrix. Okay, and that's really just your inverse of A. And then that's going to produce a decoded matrix. So I'm going to take my decoded matrix then, and if I lay them out side by side, oops, let me get back to my pen here. I see that I have 13, 5, 5, put that next to 20, 0, 13, then I have 5, 0, 13, and you're going to continue on with this. I'm going to stop right there for now. And then what you have to do now is you have to go and correlate each one of these numbers here to the letter that corresponds to that original 0 equals a blank, A equals 1, B equals 2, and so on. So 13 we know was M, 5 was E, 5 was E, 20 was T, 0 was a blank, 13 was M, 5 was E, 0 was a blank, and 13 was M, and we're going to do this for the remainder of the message. And remember, it should say, meet me Monday. Now this concludes section 8.5. You have a closing puzzle for you. In honor of Pi Day today, I want you to solve the puzzle the square root of a -1 times 2 cubed times sigma times pi, and tell me what that equals tomorrow in class. Have a good night.